Let's practice simplifying square roots of monomials together. For number 1, we have 49 times x to the 6th power times y to the 14th power. Now I think this one's a nice one to start with just because it is actually a perfect square. So 49 breaks into exactly 7 times 7. So when we go ahead and take the square root of 49, the square root of 49, that's just going to be equal to 7, right? For the next piece, we have this x to the 6th power. Now x to the 6th power is actually a perfect square too, so anything to an even exponent is going to break down into half of it, so it's x to the 3rd power times x to the 3rd power. So if you ever ask what's the square root of x to the 6th power, anything to an even exponent, it's just going to be the variable or whatever that value is raised to half the exponent as it was before, right? Because x to the 3rd power times x to the 3rd power is x to the 6th power. Lastly, we have this y to the 14th power. That's actually also a perfect square, right? Because y to the 14th power is really just y to the 7th power times y to the 7th power. So when asked what is the square root of y to the 14th power, that's just going to be y to the 7th power. That would be the square root of it. So if you're being asked what's the square root of this whole expression over here, well, the square root of 49 is just going to be 7. The square root of that x to the 6th power is going to be x to the 3rd power. And then the square root of the y to the 14th power is just going to be y to the 7th power. So this would be the square root of this monomial, or the most simplified version for this radical. Let's try another one together. So for this one, we have the square root of 80 times a to the 7th power times b to the 8th power. So we have a regular coefficient here, a number of 80. Now 80 is not a perfect square, right? So we're going to go ahead and break down 80 and see what we can find out about it if we have any perfect squares hidden inside. So 80 we can say is going to be 2 times 40. 40 is going to break down into 2 times 20. 20 can break down into 2 times 10. And then 10 breaks down into 2 times 5. All right, so we have some prime numbers here. We have a 2, we have another 2, a third 2, a fourth 2, and then we have a 5, right? So now that we have all these prime factors, we can say these two 2's make a perfect square of 4. These two 2's also pair together to make another 4, and then we have this extra 5 hanging out over here, right? So if we go ahead and say that 4 times 4 times 5, that's equal to 80, then if we go ahead and take the square root of 80, that's the same thing as root 5 times root 4 times root 4. Now, root 4 is equal to 2, root 4 is equal to 2, and we have a root 5. So 2 times 2 is 4. So this is really just the same thing as 4 times the square root of 5, right? That's the most simplified radical for the square root of 80. Now, moving on to this a to the 7th power, we can go ahead and break down a to the 7th power like this. We can say, okay, a to the 7th power is equal to a to the 6th power. Always just drop one exponent or one power or 1 degree. And so that's going to be a to the 6th power times a to the 1st power. So if you go to take the square root, the reason why we drop down for odd numbers is because even numbers are perfect squares, right? So the square root of a to the 6th, that's going to be a to the 3rd power. And then a to the 1st power is not a perfect square, so that's going to stay as a. Finally, we're going to take a look at this b to the 8th power. So if we take b to the 8th power, notice that it's already raised to an even exponent. And so the square root of b to the 8th power is really just going to be b to the 4th power. So if you remember from earlier, it's just going to be half of all even numbers. So if we know the square root of a to the 6th is a to the 3rd, then the square root of b to the 8th is just b to the 4th. Okay. So let's now go and combine a few things here. So if we have the square root of this 80, a to the 7th, b to the 8th, well, let's see what came out here. We have 4 on the outside and a to the 3rd on the outside and b to the 4th on the outside. So that's going to be on outside this 4. Okay, that's on the outside. Then we have a to the 3rd power that also came out as a perfect square. Then we're going to have b to the 4th power that also came out as a perfect square. And then what's left on the inside? Well, those are the 3 things that get to come out. But what's still inside here? We have a 5 and an a. So we're going to leave the 5 on the inside and leave the a on the inside as well. So this would be the most simplified or simplified radical for this monomial expression. Let's try number 3. For number 3, we have the square root of 72, x to the 10th power, y to the 17th power. Let's start with the 72. So 72, we can break this down into some smaller factors. Let's maybe start with 8 times 9. This 8 can break into 2 times 4, and 4 can break into 2 times 2. And over here, this 9, we can say that's 3 times 3. Okay, so we have 2 as a prime, 2 as a prime, another 2, and then we have these 3's over here, right? So let's see, what perfect squares do we have? Well, 2 and 2 make 4, that's a perfect square. Then 3 and 3 make 9, that's a perfect square. So 4 times 9, then we have this extra 2. That's not a perfect square, but this equals 72. So if that's true, that means the square root of 72 is the same thing as root 2 times root 9 times root 4. Okay, the square root of 4 is going to be 2. The square root of 9 is going to be 3. So we have 2 times 3 times root 2, and 2 times 3 is 6. So the square root of 72 is the same thing as 6 times the square root of 2. That's the most simplified version for this part, or the number, okay? So we have this x to the 10th power. Let's go ahead and take x to the 10th power. Keep in mind, if we take the square root of any even power, then the square root of x to the 10th just becomes x to the 5th, because x to the 5th times x to the 5th is x to the 10th. And then this y to the 17th power, what I recommend that you just think about is, okay, 17, that can break into y to the 16, right? That's 1 less. And then you go ahead and put the 1, that y to the first power by itself, right? Because what's the square root of y to the 16th power? That's just y to the 8th power times y. All right, so again, whenever you have an odd exponent like 17, just try to break it up into 16 and 1, okay? And then you can take the square root of y to the 16th power. That would just be y to the 8th power here. All right, so let's see what came out of the radical. This 6 got to come out, this x to the 5th, that was the square root that got to come out, and then this y to the 8th power. So for our answer here, let's put 6 on the outside. We can also put that x to the 5th power because that was a perfect square root, and then y to the 8th power. All right, so those are the things that got to come out here. This 6 was in front, this got to come out, this got to come out. Okay, now what didn't get to come out? What were the non-perfect squares? Well, let's start with the number first. There was a 2. 2 goes on the inside still. And it looks like we just have a y that's also stuck on the inside, right? So that's going to be our most simplified radical. That 2 and y have no perfect square factors left. So this would be the most final or most simplified expression. For number 4, we have the square root of 288a to the 13th power times b to the 8th power. So let's look at this 288 for a moment, okay? This 288, let's see if we can go ahead and break that down. It's a pretty big number. We can say it's going to be 2 times 144. So if you recognize that we have a perfect square along the way, you could keep going and then pair up all the values that you want, but 144 times 2 equals 288. But keep in mind that if we know that 144 is a perfect square, then we can go ahead and just say that 144 or square root of 144 times square root of 2 equals square root of 288. Now the square root of 144 is 12, so this is just 12 root 2. That would be the most simplified version for the square root of 288. Okay, and again, if you want to go ahead and write it out to get that, feel free to go ahead and write more steps out. Now a to the 13th power, now that's an odd exponent, right? So let's take away 1. So let's make that a to the 12th power times a to the first power. That would still be equal to a to the 13th. So if you took the square root of this, the square root of this, and square root of this expression, or equation rather, is still going to be the same. The square root of a to the 12th is going to be a to the 6th. And then we have a to the first power. That's not a perfect square, so that stays inside. Then we have this b to the 8th power, right? If we have b to the 8th power and you're taking the square root of it, since it has an even exponent, then it's a perfect square. The square root of b to the 8th power is b to the 4th power. Okay, so let's see what came out. This 12 got to come out, right? That is now not inside the radical. This a to the 6th power is out, and this b to the 4th power is out. So 12's on the outside, a6 or a to the 6th power rather, it's on the outside. B to the 4th power is also on the outside. Let's see what's stuck inside this root 2 and root a. So let's go ahead and say this is going to be root 2, that goes on the inside, and then a, that goes on the inside as well. So this would be the most simplified expression that we could write here. Here's number 5. For number 5, we have the square root of 75 x to the 7th y to the 19th. So let's just look at the number 75 first. So 75, if we go ahead and try to break that down, we can see that we can maybe start with, I don't know what you might choose, maybe 3 times 25. But I'm noticing here that 25 is already a perfect square. So maybe we can say that 25 times 3 is equal to 75, right? So if that's true, we can say the square root of 75 is equal to the square root of 3 times the square root of 25. The square root of 25 is 5, so this is going to be 5 root 3, right? And I don't think we can simplify any more. For this x to the 7th power, let's go ahead and break that down, right? That's an odd number, so let's take away 1 from the exponent, so that's x to the 6th power times x to the 1st power. That's equal to x to the 7th power. And then we can go ahead and just take the square root, say the square root of x to the 7th is the same thing as the square root of x to the 6th times the square root of x to the 1st. Now the square root of x to the 6th power is just x to the 3rd power times this x to the 1st power, the square root of it just stays the same, right? That's not a perfect square. And then we have this y to the 19th power. So that's also an odd exponent. So y to the 19th, if we take away 1, that's y to the 18th times y to the 1st power. So the square root of y to the 19th is the same thing as square root of y to the 18th times the square root of y to the 1st. The square root of y to the 18th is just y to the 9th. And then we still have this extra y that's stuck inside here, right? So what got to come out? Well, we have the 5, we have the x to the 3rd, and we have the y to the 9th. Those are the three things that were perfect squares that could come out. So we had that 5 there, and then we have this x to the 3rd power, and then y to the 9th power. And then there were a few things that got stuck inside the radical, right? Because they were not perfect squares. So this 3 is the first thing. Let's go ahead and put this 3 still inside. That wasn't a perfect square. Then we have this x and this y that were not perfect squares either. So let's put an x, and then let's put a y. So this right here we can see would be our most simplified expression. For number 6, we have the square root of 160 a to the 16th b to the 7th power. So let's look at this 160 first. So 160 can break into, I don't know, maybe like 2 times 80. And then 80 can break into 2 times 40. 40 can break into 2 times 20. 20 can break into 2 times 10. And 10 can break into 2 times 5. So we got some prime numbers here. We have a 2, another 2, another 2, another 2, another 2, and a 5. So let's see what perfect squares we have. We have 2 and 2, that's going to make 4. We have another 2 and 2, that's going to make another 4. Finally, we have a 2 and a 5, and neither of them had any pairs, so we're going to keep the 2 and the 5. This all equals 160 if we multiply them together. So the square root of 160, and then we have the square root of 4 and the square root of 4. I'm going to put these two together since they don't have partners, right? The square root of 4 is 2, the square root of 4 is 2, and 2 times 5, that's going to be just root 10, right? Because those ones didn't have partners. And then so 2 times 2 is 4, so 4 root 10 is the same thing as the square root of 160. For a to the 16th power, this one's kind of nice because it is an even exponent. So the square root of this is just going to be a to the 8th power because it's just half. Remember, a to the 8th times a to the 8th is a to the 16th. Now this b to the 7th power, let's go ahead and just break that up into, take away 1, that's b to the 6th times b to the 1. And if you take the square root of b to the 7th, that should be the same as the square root of b to the 6th times the square root of b to the 1. The square root of b to the 6th is going to be b to the 3rd, and then we have the square root of b afterwards. Okay, so let's see, what got to come out of the radical? It looks like a 4, and the a to the 8th, and the b to the 3rd. So let's put a 4 in front, then we have a to the 8th power, and then b to the 3rd power. Those are all the things that got to come out because they were perfect squares when we were inside. And then what's on the inside looks like a 10 and a b. So let's go ahead and put a 10 in front and then a b afterwards. This would be the most simplified version for this radical. Let's look at number 7. For number 7, we have the square root of 567, x to the 8th power, y to the 14th power, z to the 5th power. Let's start with this 567 we have in the beginning. That's a pretty big number here. So 567, I'm trying to think what this is divisible by. 5 plus 6 is 11, plus 7 is 18. So 18 is a multiple of 9. So we can divide this by 9. If we divide this by 9, I believe that is going to be 63. And then that means 9 can break into 3 times 3. 63 is more manageable. We can say like 7 times 9. And then 9 can break into 3 times 3. All right, so we can see our prime factors here are going to be 3, 3, 7, 3, and 3. And then let's see what they have in common. So 3 and a 3 make 9. That's a perfect square. 3 and a 3 make 9. That's another perfect square. And then this extra 7 is just kind of hanging out. And this equals 567. All right? So the square root of 567 is going to be the square root of 7 times the square root of 9 times the square root of 9. That's going to be 3 times 3 times root 7. And 3 times 3 is 9, so this is just going to be 9 root 7, right? That would be the most simplified version of the radical there. Now for this x to the 8th power, right, the square root of x to the 8th power is just going to be x to the 4th power because it's half of that. Then let's go on to this y to the 14th power. The square root of y to the 14th power, that's also an even exponent. That's going to be y to the 7th power. And then let's see what to do when we have an odd one, right? Let's see if this makes sense. If we take the z to the 5th power and we take the square root of it, let's see if this makes sense to you, but we will then break this down into the square root of z to the 4th power times z to the 1st power, and the square root of this and the square root of this. The square root of z to the 4th is just z squared, so z squared times z. Okay, so let's see what got to come out. It looks like this 9 comes out, this x to the 4th, y to the 7th, and z squared all get to come out. So let's go ahead and write those. Let's have 9, and then we have x to the 4th power, the 4th power like that. Let's do y to the 7th power. We have z to the 2nd power. And let's see what was stuck inside still that didn't have partners. Let's put a 7 in here, and then let's put a z. All right, so this would be the most simplified radical. All right, for number 8, we have the square root of 252, a to the 9th, b to the 16th, c to the 5th power. Starting off with this 252, that's a pretty big number, so maybe we can break it down into some smaller numbers. If we break that down, I think that's going to be 9 times 28, just because 2 plus 5 plus 2 is 9, so we can divide it by 9. This 9 breaks into 3 times 3. This 28 breaks into 7 times 4, and 4 breaks down into 2 times 2. All right, so we have a 3, a 3, a 7, a 2, and a 2. So these 3's pair together to make a 9, that's a perfect square. 2's pair together to make 4, that's another perfect square. And then we have this extra 7. And if you multiply these, you do get 252, right? So the square root of 252 is the same thing as the square root of 7 times the square root of 4 times the square root of 9. The square root of 9 is 3, the square root of 4 is 2. We have this root 7. So 3 times 2 is 6, so we have 6 root 7. So that takes care of the number. For a to the 9th power, let's see if you're getting the hang of this. A to the 9th power, the square root of it, if we take 1 away, that's a to the 8th power. So the square root of a to the 8th power is going to be a to the 4th power, but we have an extra a because we had an odd exponent. Okay. If we have b to the 16th power, if we take the square root of this one, that's an even exponent, so the square root of b to the 16th power is just b to the 8th power. It's a perfect square. And then finally the c to the 5th power. Unfortunately, that is an odd exponent, so something's going to be stuck inside. So if we take away 1, that's c to the 4th. The square root of c to the 4th power is going to be c to the 2nd power. And then we still have an extra c that doesn't get to come out here. Okay, so see if that makes sense. If not, go ahead and write it out with a couple extra steps like we did in the earlier problems. Now what came out, it's this 6, a to the 4th, b to the 8th, and c squared. So let's go ahead and put the 6 on the outside, a to the 4th also along the outside, b to the 8th, that's on the outside, and then c squared. Those are all the perfect squares. Then let's see what was still on the inside. We had a 7, an a, and a c. So let's put 7 in there, let's put a in here, and let's put c in here. All right, so one of each variable was still stuck inside. For number 9, we have the square root of 360, x to the 14th, y to the 20th, z to the 7th. Let's start with this 360 here. So if we go ahead and break this down, maybe we can start with 2 times 180. 180, maybe we can do like 10 times 18. Then 10 is going to break into 2 times 5. 18, we could say something like 2 times 9. And then 9 could break into 3 times 3. So let's say we have a 2, we have a 3, a 3, a 2, a 2, and a 5. Let's see here, the 2 and the 2 are going to make 4, that's a perfect square. 3 and 3 make 9, that's another perfect square. 2 and 5 are going to be our extras, 2 times 5, And then so all of these multiplied together equals 360. All right, so if we take the square root of 360, that's going to be the square root of each of these individual factors. The square root of 4 is going to be 2. The square root of 9 is 3. The 2 and 5 have no partner, so we just combine those back to make 10 and put it in the radical. Then 2 times 3 is 6. We have 6 root 10. Okay, that's a square root of 360 simplified. Now for x to the 14th power, if we go ahead and take that, if we take the square root of x to the 14th power, it's an even exponent, so it's just x to the 7th power. Then if we go ahead and try the square root of y to the 20th power, well, that's also an even exponent, so the square root of y to the 20th power is just y to the 10th power. And then finally, for z to the 7th power, if we take the square root of that, that's an odd exponent. So if we take away 1, that's z to the 6th power. The square root of z to the 6th power is z to the 3rd power, right? And then we have one extra z hanging out inside here because it didn't have a partner. So the things on the outside are the 6, the x to the 7th, the y to the 10th, and the z to the 3rd. So I'm going to go ahead and write 6 on the outside, x to the 7th power, y to the 10th power, z to the 3rd power. All of these were square roots. And then what's on the inside? It looks like it's 10 and z. So inside the radical here, we're going to have a 10 and a z. All right, so there we have our most simplified radical. Here's number 10. For number 10, we have the square root of 288a to the 8th power, b to the 17th power, c to the 12th power. Now 288, I think we've actually seen before. So 288, if we divide that by 2, that's going to be 2 times 144, right? 144 multiplied by 2 is equal to 288. And if we go ahead and take the square root of 288, that's a square root of 2 times the square root of 144. Root 144 is 12, so we have 12 root 2. Okay, that's a square root of 288. For the square root of a to the 8th power, if we take that a to the 8th and take the square root of that, it's an even exponent. So the square root of that is just a to the 4th power. Then if we take a look at this b to the 17th power, this one is raised to an odd exponent. So take away 1, that's b to the 16th power. But the square root of b to the 16th is going to be b to the 8th. That's just half of that exponent. And then we have an extra b. Okay. Then finally, this c to the 12th power, that one's nice because it has an even exponent. So it's a perfect square. The square root of c to the 12th power is just going to be c to the 6th power. So what comes out looks like a 12, a to the 4th, b to the 8th, c to the 6th. A lot of stuff's coming out here. So we have 12, a to the 8th power. Sorry, just kidding. A to the 4th power, b to the 8th power, and then c to the 6th power. All right, those are all perfect squares, and on the inside we should have a 2 and a b. So let's go ahead and write the square root of 2 times b. And this should be the most simplified radical here. Let's check out number 11. Number 11, we have the square root of 320, x to the 8th, y to the 12th, z to the 14th power. Let's see here, we have 320. Let's go ahead and see if we can break that down. I know we can do 10 times 32. Okay, now 10 we can break into 2 times 5, and those are done. For 32, we can do maybe 2 times 16. For 16, we have 2 and 8. For 8, we have 2 and 4. And then 4, we can say that's 2 and 2. So that's prime, another prime. We have a bunch of little primes here. And so let's see if we can find some perfect squares. So 2 and 2 make a perfect square. 2 and 2 make a perfect square. 2 and 2 make another perfect square. And we have this extra 5 kind of hanging out here. That equals 320, right? So the square root of 320 is equal to the square root of 5 times the square root of 4 times the square root of 4 times the square root of 4. The square root of 4 is 2, so we have 2 times 2 times 2 times root 5. 2 times 2 is 4, 4 times 2 is 8, so this is 8 root 5. Okay, moving on, this x to the 8th power, this one's actually nice. X to the 8th power, the square root of that is just going to be x to the 4th power. Okay, it's half of the exponent. Y to the 12th power, if you want to take the square root of the y to the 12th power, that's going to be y to the 6th power. And then we have z to the 14th power. If we want to take the square root of z to the 14th, that's going to be z to the 7th since it's an even exponent. Okay. A lot of stuff came out. There looks like this 8, this x to the 4th, y to the 6th, z to the 7th are all going to come out. So we have 8, and then x to the 4th power, y to the 6th power, z to the 7th power. And the only thing stuck inside looks like this root 5 here. So we're going to keep the square root and then put this 5 so it's stuck inside. Okay, didn't get to come out, didn't have any partners to come out from the square root. That would be the final expression. Number 12, we have this square root of 144, a to the 19th, b to the 15th, c to the 27th power. And so let's think about this 147, right? So 147, if we go through maybe our divisibility, I think we can divide this by 3, just because 1 plus 4 is 5, and then 5 plus 7 is going to be 12. So 147 divided by 3, I think is going to be 49. And I think we can just stop there because 49 is a perfect square. So 49 times 3, that's 147. And so 49, the square root of that is 7, I'm thinking, right? So the square root of this times the square root of this. So the square root of 49 is 7. So we really have 7 root 3, right? That's a square root of 147. Now, a little annoying here, but we have a bunch of odd exponents. So we have a to the 19th power, and we want to take the square root of that. Take away 1 from 19, that's 18. So the square root of a to the 18th power would be a to the 9th power. And we have 1 extra a stuck inside. Then we go over to this b to the 15th power. If you go ahead and take the square root of b to the 15th, take away 1, that's b to the 14th. The square root of that is going to be b to the 7th power. There's going to be an extra b. And then finally, this c to the 27th power. We take c to the 27th to take the square root. Then that's an odd one, so take away 1, that's c to the 26th power, but half of 26 is 13, so the square root of that is c to the 13th power, and there's an extra c kind of hanging out inside there. So what came out is the 7, the a to the 9th, the b to the 7th, the c to the 13th. Those are all the square roots. So let's do 7, a to the 9th power, and then b to the 7th power, and then c to the 13th power. And let's see what was inside. Looks like inside here we had a 3a, b, c. So let's take a 3 and then put an a times b times c. I'm just going to go ahead and fix this 7 because it's kind of messy. So let's put a 7 here so you can see a little bit more clearly. And I'm going to fix this a to the 9th, so that's a little bit more clear too. So this would be our most simplified expression. So there you have 12 different practice problems on simplifying monomial radical expressions. Keep in mind that anytime you're dealing with these, try to deal with the numbers separately. If you have even exponents for the variables, they are perfect squares, so they come out perfectly with nothing left inside. But if they're odd exponents, just take away 1 from the exponent, then it's a perfect square, and then leave whatever's extra on the inside of the radical. If you found this video helpful, please consider giving it a thumbs up. And as always, keep up the great work, and I'll see you in the next one.